Hello, good evening. Welcome everyone to the problem solving session class for NPTEL online course on wastewater treatment and recycling. We are in week 5 and I'm Akash Shah, one of the teaching assistant for this course. I am a PMRF scholar in the Department of Civil Engineering pursuing my PhD in environmental engineering at IIT Madras. So we are into week 5 and in week 5 we have seen the following topics starting from the basics of municipal wastewater treatment where we learnt about the objectives, the discharge standards, the reuse standards and many different types of unit processes and operations. Then we move on to the first treatment process, that is the screening. We learned about the various types of screens, the communicating devices, the location of screens, and the related hydraulics. At last, we calculated the head loss through the screens. And then we moved on to the topics related to grit removal and equalization tank, and we saw the design aspects of that. And in the at the end, we learned about the primary sedimentation and the related concepts. So this was the whole overview of the week 5. So I have some subjective as well as objective questions related to this week 5. So we will start with the subjective type numericals because we are much familiar with the other aspects. So let's see. I will show you the question. Just go through the question once and try to solve the problem, and then I will show you how to solve the problem step by step. So this is the first problem. I hope I am audible. Hello. Okay. So this is the first problem. This is the first problem which says that you have to design a bar rack and screen chamber for a peak design flow of 150 mld with the following data. So you have this peak design flow and some details related to the incoming sewer line that is coming to the screen chamber. So we have the diameter of the sewer line, that is 1.4 meter. We have the depth of flow of water in the sewer line, and then we have the velocity of flow in the sewer line at peak design flow. So everything is given as per the peak design flow. And then the drop of screen chamber to the invert, and then the assumed width of the rectangular bars which will be provided as screens, that is 10 mm, and the clear spacing between the bars. So this is the overall data given for the problem, and with respect to it we have to design the bar rack and the screen chamber. So try to picturize the problem at first, like how the sewer line and the bar screen will look, and then we can move on to solving or designing the screen chamber. So go through the question once again. We will solve it one by one. Kindly note down the parameters which are given in the question in your notebook because I will be changing the screen. So just note it down, the parameters, and then we will start solving the question. If you have noted down, just send a thumbs up so we can move forward. I'll wait for 30 seconds. Are you able to understand the problem? Shall we move forward? Have you written down the problem? Hello. Guys, please respond if you are done with noting down the details regarding the
Sir,
problem.
I'm noting.
Okay. Just send a thumbs up if you are done. So if we solve the problem, we will be able to get an idea about everything related to the designing of a screen chamber. So it's a wholesome problem. or you can just take a screenshot of this problem. Okay. Saket, shall I move forward?
Okay.
Okay. Okay. So first of all, I will show you the diagram, like how this problem looks. So suppose this is the sewer line that is coming, and below that we have the area for the screen chamber. Okay, this is the sewer line. So the diameter is given as this is 1.4 meter. Okay, and the invert level of this sewer line and the base of our screen chamber area is zero point 0.8 meter. This is given. And suppose this is the depth of flow of water. Here is the screen and it will be like this. So the water depth in the sewer line is given as 1.05 meter. Okay, suppose I am taking this line as my datum. So this will become my Z1. This is the first cross section I am taking. This is the second cross section. This is the third cross section. So we have a cross section at the sewer line first. We have a cross section before the screen, that is the upstream of the screen, and we have a cross section downstream of the screen. So in the sewer line, the datum head is Z1. At section 2, we have Z2. At section 3, we have Z3. Is it clear? Are you able to visualize the problem? Guys, please respond. Or if you want any clarification. Hello.
Sir, explain one time, please.
See, are you able to visualize that this is the sewer line? Okay, that is the pipeline which is bringing the sewage into the system. And this is the start of my screen chamber area. Okay, and this is my screen. Suppose this is my screen. So water is flowing in this direction. Okay, so we have been given the diameter of the sewer network as 1.4 meter. Okay, and the difference between the level of this screen chamber and the uh, invert of the sewer line as zero point 0.8 meters. This is the difference between the screen chamber baseline and the invert of the sewer. So that is zero point 0.8 given in the question, right? It's all given in the question. Okay, oh, sorry, it's 0.08, I think. Not zero point 0.8, it's 0.08. Right? Okay, 0.08. And then we know that the depth of water inside the sewer line, because water is flowing from here, it will go like this. So the depth of water inside the sewer line is 1.05. So that's what I have shown, 1.05. This depth of water we have to calculate. Like what is the depth of water before the screen and what is the depth of water after the screen, D3 and D2. Because after passing through the screen there will be some head loss, so my depth of water will decrease. Okay, is it fine? Okay, so now our first target is design of the bar rack. So first of all, we have to assume a velocity of flow through the rack openings. here we have the racks. This is my rack. So through this, what will be my velocity? So assume velocity of flow through rack openings is equal to 0.9 meter per second. So we are basically just assuming this range can be 0.6 to 1.2 meter per second. So I am assuming it to be 0.9 meter per second. So what will be my clear area of openings? Through rack will be equal to the discharge divided by the velocity. So my discharge is given as 1.736 and velocity I have taken it as 0.9. So my area will be 1.929 meter square. So this is my clear area through the rack. Okay. So this will be my clear area through the rack. Now I know that so this is my clear area. Now clear width. Clear width of opening. Through racks will be my area divided by the height. So it will be 1.84 meter. So I got the clear width. So number of clear spacings required will be the clear width divided by the width of each spacing. So the clear width of each spacing is given as 25 mm. So that is equal to 0.025 meter. So my number will be approximately equal to 73. So this is the number of clear spacings required. Are you able to follow this much? Okay. So I hope you are noting down. I will erase it now. So now we know the clear width. So the number of bars. So we have to provide from last statement. We will provide 73 clear spacings of 25 mm each. So this is my clear spacing. So number of bars will be equal to, if spacings are 73, so number of bars will be 72 of, and we know the width of each bar is 10 mm, 10 mm each. So we have the clear spacing 73 of 25 mm each, and number of bars will be 72 of 10 mm each. This is given in the question. So the total width of the screen chamber will be equal to 73 into 0.025 plus 72 into 0.010. So that will be equal to 2.545 meter. So is it okay? So we now got the total width of the screen. So if I, so this rack, if I am viewing it from the direction of water, So suppose this is my area. So this colored portion will be my racks. Okay. Water is flowing into the channel. Suppose water is flowing into the screen. So it will look like this. This clear width is 2.545 meter. And this is all my rods of 10 mm each. And the clear spacing here, it is 25 mm. So we have this type of rods as 72 numbers, and this spacing as 73. So are you able to visualize the problem now? So like this way, we will design the bar rack. So we have to find out the total width, the clear width, the number of clear spacings, and the number of bars. Is it okay? Okay. Okay. Others, you can also ask any questions if you have. This is a simple problem. Okay, so this was the first part of the problem where we have designed the bar graph. Now we will find all this. Uh, so we will now find what is would be my D2. Okay, so if we have to find D2, what we will do? We will apply energy conservation at point 1 and at point 2. So we will apply the. So which theorem will be applicable for energy conservation? Can you tell me? Hello, am I audible? So if I want to find the this depth D2 by conserving the energy at point 1 and at point 2, so which theorem have to apply? We have to apply. Anyone? So we will apply Bernoulli's theorem. Okay. So as per Bernoulli's theorem at 1 and 2. So that Z1 plus D1 plus V1 square by 2G will be equal to Z2 plus D2 plus V2 square by 2G plus head loss. Are you aware of this energy conservation theorem? Hello, Satvik, Serena, Saket, anyone aware of this theorem? You have to respond or else I will not be able to move forward, guys. Okay. Okay, I will give a brief introduction to this theorem. So as per this theorem, if we take any 2 points in a system, like in this I have taken this point 1 and point 2, so the total energy will be conserved. Okay, so energy here we are taking in terms of head, whether it will be my potential head or velocity head or datum head. So it will be conserved at any point 1 and 2. So the total energy, so my total energy in terms of hand will be my datum head that is Z, what is the distance from this area, then my water depth, that is the D, and then my velocity head, which is v square by 2g. So at any position, if we, and then is if there is some losses are there, we have to plus minus losses. So we have to see the losses also. So in this way, the total energy can be conserved in the in both the systems. Okay, you can learn. I will show you the application of this. So here the head loss HL, the head loss HL will be calculated as KE into V1 square by 2G minus V2 square by 2G. Okay, so this is the head loss due to sudden expansion from sewer to the screen chamber. Okay, because of this head loss, there will be, because of this sudden expansion, there is some X cross. And here the Ke value, which we generally take is as zero point 0.3. I hope you have noted down. Okay. Okay, so now we will apply. Now at first Z1. Z1 value is my distance from the datum, this distance from my datum to the invert layer of my first point. So my Z1 will be equal to, it is given in the question as 0.08. And what will be my D1? D1 will be the depth of water in the sewer line, that is 1.05. And then V1 square by 2G, I know the velocity inside the sewer line as 1.16, so 1.16 square divided by 2.81, 2 into 9.81. Now Z2, 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 I will approximate to at 0. Instead of datum, taking the datum line here, I can also take the datum line here. Okay. So in this case, my Z1 will become this and my Z2 will become 0. Okay. So it will be 0 plus D2 plus now V2 square. So in this area, what will be my velocity? My velocity will be Q 7.36 divided by area. So my width is 2.454545 into D2. So this will be my velocity divided by 2 into 9.81. And then the head loss. My head loss will be, as I told you, 2 into 9.81 into 1.16 square minus 1.736 divided by 2.545 d2 the whole square. So this is the equation we have to solve and get the d2. Okay. So if we solve the equation, we will get d2 as 1.17 meter. Is it okay? Saket, are you able to understand? Which part you are not able to understand? Please tell me. I will try to explain. Which part is not properly understood?
When we put the value of VT square by 2G plus HL.
Okay, V2 square by 2G. Fine. I will show it once again. V2 square, right? So what is V2? V2 will be Q divided by the area, right? In the in which portion? In this portion. In this portion. Okay. So Q is same. Q will be 1.36, 1.736, right? So Q will be 1.736. And now the area we know it is the width into depth, right? So width we have just found out as 2.545, right? If you check your previous answers, you have just found out the width as 2.545, and depth we don't know. Depth is d2. So is now v2 clear? So from here v2 square by 2g will become 1.736 divided by 2.545 into d2 ka whole square divided by 2 into 9.81. Is it fine, Saket? Okay. Similarly, we will similarly for HL. What is HL? HL is KE into V1 square by 2G minus V2 square by 2G. So KE I have told you as zero point 0.3. I am taking the 2G outside, that is 2 into 9.81 into, now V1 square is remaining. V1 we know it has 1.16 square given in the question, and V2 square again 1.3736 2.545 D2 ka whole square. So this will be my HL. So if I put all these parameters into my equation, I will be getting my D1. I hope it is fine now. Okay. So we have got, sorry, we have got D1 as, sorry, D2 as 1.17 meter. So if I know D2, my V2 will be equal to 1.736 by 2.545 into D2. D2 is 1.17. So it will be 0.583 meter per second. Now it is clear, right? So in the second portion, the velocity will be 0.583. Okay, I will rub it everything. So again, I will just roughly draw the diagram. So this is the sewer line. This is my screen chamber. Okay, so we have found D2, which is equal to 1.17. So this is the depth of water before, and my velocity before is 0.583 meter. Okay, so now we will find out the velocity through the bar rack. So that velocity through bar rack. Bar rack clear opening. So my V will be equal to Q by area again. Area clear. That is the clear area. So 1.367 divided by what is the clear area? So again we will do width into depth. So what will be my clear width? My clear width will be 73 into 0.025. Why? We have 73 number of clear spacings and the each clear spacing is of 25 mm. So my total clear width will be 73 into 0.025. And what will be my depth? My depth, I have just found out, will be 1.17. Right? So here my velocity will become 0.89, 0.813. So if you remember in the starting of the problem, we have assumed it as zero point 0.9, the velocity through the bar rack to be zero point 0.9 meter per second. But here we are getting it as 0.813, which is almost equal to zero point 0.9. So we will not change anything. So our actual velocity of flow through the opening of the bar rack will be 0.813 meter per second. Right. So now we will find the head loss. So for head loss, there is a direct formula 0.079. Whereby what is the velocity through the bar rack screen minus what is the approach velocity. That is my V2 square. So it will be 0.079 into 0.813 square minus 0.583 square. This is the same V2 that we have. Okay. So that will be equal to 0.0234 meter. So this is my head loss. So are you able to follow everyone? I hope it is fine now. So at each position, we have to find the depth of water, we have to find the velocity. For finding the velocity, we will divide the flow with the area, whatever area. If it is bar rack area, we will divide with the area of bar rack. If it is clear spacing, we will divide by the clear spacing area or whatever will be the respective area. So in this way, we will be able to find the velocity and depth at each of the position. And at last, we will check the head loss. So my head loss should not be, my HL should not be more than 150 mm. Okay, which is equal to 0.15 meter. So it is fine. So my design is okay. So now shall we move into the next problem? Is it okay? Can we move to the next problem? Okay, great. So this is the next problem. Again, it's a problem related to screen chambers. So a water with a design flow rate of 300 liter per second is passing through a rectangular channel, has a maximum flow velocity of 36 meter per minute. A core screen is to be installed in the channel using 10 mm thick bars with 30 mm clear openings and at an inclination of 50° to the direction of flow. Determine the velocity through bars and head loss in meters. You have to find the velocity through the bars and the head loss like we did in the previous question. So assume the width to depth ratio of the channel as 1 is to 1.5 and the coefficient of discharge as 0.7. So this is my overall problem. Go through it once again. We will solve the problem now. Just for 30 seconds, you can go through the problem. Okay, I hope you have taken the screenshot of the problem. We will try to solve it now. Okay, so it was given that my discharge is 300 liter per second and velocity as 36 meter per minute. Okay, and the width to depth ratio is 1 is to 1.5 and C coefficient of discharge is 0.7. So these are all the parameters given. So first, what is my velocity of approach? Velocity of approach is 36 meter per minute. I will change into 2 seconds. 60 second per minute. So it will be equal to how much? 0.6 meter per second. So what will be my area? My area will be Q by VA, which is equal to 300 liter per second means 300 liter per second means 0.3 meter cube per second divided by 0.6 meter per second, which will be equal to 0.5 meter square. Okay, now we know the width is to depth ratio as 1.1 is to 1.5. So my total area AC, which is equal to zero point 0.5, will be equal to width into 1.5 times of width. That is the depth. This is my depth. So, so from here we can get 0.5 is equal to 1.5 W square, which will give my W to be equal to 0.577 meter. And if I know the W, my depth will be 1.5 into W. That will be equal to 1.5 into 0.577 equal to 0.833 meter. Okay, fine. Now here we have been given that the bars are inclined. The bars are inclined at 50 degree. So my effective area of screening will increase. So what is my increased area? Suppose AS will be equal to AC divided by sine 50 degree. So it will be zero point 0.5 divided by sine 50 degree, which will be equal to 0.653 meter square. Is it okay? Guys, it is okay till now? It is a very simple problem. Anything which you are not able to understand, please tell me.
Okay, sir.
Okay. So the area which we found, the total area will be 0.653 meter square. Now we have to find the net area. Okay, because there are some openings and some bars, so we will find the net area. So my net area will be equal to the total area that we got into the spacing divided by spacing plus diameter. So it is basically with respect to ratio. So my spacing by spacing plus diameter ratio will get the net area. So my AS will be equal to 0.653. My spacing was given as 30 mm. So 0.030 divided by 0.030 plus what is my diameter? Diameter is 10 mm. So 0.010. So if I find the ratio and the spacing, so my net area will be equal to 0.49 meter square. Okay. So this will be my A net. So since we have found the area net, we have to find the velocity of flow through the screen, because the velocity of flow through the screen will be through the area net. So by simply we will apply the continuity equation. That is my velocity of flow into the actual area will be equal to velocity of flow into the net area. So my velocity of flow will be equal to zero point 0.6 into zero point 0.5 divided by 0.49. So it will be 0.612 meter per second. Okay, so this will be my velocity of flow. And at last, the head loss. So head loss will be 1 by C into Vf square minus Vs square by 2G. So 1 by 0.7 into 0.612 square minus 0.6 square divided by 2 into 9.81, which is equal to 0.0011 meter. So this is my head loss and the velocity. So we have found both the parameters, the velocity through the screens and the head loss. So we have incorporated the factor 1 by C because in the question it is given the coefficient of discharge as 0.7. If it is not given, we will not take this factor. So because of this factor only, we are considering here in this problem. In the previous problem, we didn't have anything like this. Is it fine? Anything you want clarification for? Hello. Anything you are not able to understand? Or please tell so that I can move forward to the next question. Others? Abdul, is the problem okay with you? You joined midway in the last problem. This problem is fine?
It is okay.
Okay, okay, fine. Okay, so we'll move to the next problem. So these were the answers 0.612 and 0.0011 m. Okay, so now the next question is related to the design of grid chamber. So a grit removal facility is to be designed to treat a flow of 18,800 meter cube per day. The length, width, depth of the channel are 18.73 and 1 meter respectively. We have to calculate the overflow rate, the terminal velocity Vt of the smallest particle that will be fully removed, horizontal velocity, and the detention time. So kindly note down the problem. We have a grit removal facility for which the design flow is given, and then we have the length, width, and depth of the channel. So so we have to find four parameters. All are single line problems, so it will be easy for you. Okay, we'll solve the problem now. So in this question, the Q is given as 18,800 meter cube per day. Okay, L is equal to 18, width is equal to 0.73, and depth is equal to 1 meter. So these are my parameters. So my first is to find the overflow rate. Okay. So first, what will be my surface area of the channel? That will be, for overflow rate, we have to see the top, the plan of the channel. So my plan of the channel will be L into W, right? So that will be 18 into 0.73, which is equal to 13.14 meter square. So this is my surface area of the channel. So my overflow rate will be Q by A, that is 18,800 divided by 13.1 meter square, and it is meter cube per day. So it will be 1431 meter cube per meter square day. Right? So pretty simple. So for overflow rate, we have to divide the discharge with the plan area. So my plan area will be L into W. Okay. So the next part is the terminal velocity. So my terminal velocity Vt will be same as my overflow rate, because the terminal velocity of the smallest particle at 100% efficiency will be equal to my overflow rate. So I will just change it into meter per second or meter per minute into d by 24 by 60. Okay, so I'm changing it to minute. So it will be around 1 meter per minute, or we can also write it in terms of meter per second, which will be equal to 0.17, 0.0. 0.17 meter per second. So my terminal velocity will be equal to my overflow rate for the smallest particle if it is at 100%, removed at 100% efficiency. Fine. Shall I move forward? Is it fine? Just give me a reaction. Okay. Now, now the horizontal velocity. So horizontal velocity means in this direction. So in this direction, what will be my area? My area will be equal to the width into the depth. So if this is the channel, this is the channel, or how should I show you? Yeah. Suppose this is my grid chamber. This is the length, this is the width, and this is the depth. Okay. So for surface overflow rate, we have to see this area. That is the plan area. That is the length into the width. Okay. But for horizontal velocity, we have to see this area. This area, because horizontal velocity. So perpendicular to the area. So this is my area. So my area will be width into depth. Are you able to visualize it? Fine. So for horizontal velocity, we have to see the width into depth. So my velocity will be equal to q by width into depth. So 18,800. I will change it to seconds. So 1 by 24 into 60 into 60 divided by the width, that is depth, that is 1 meter, and width 0.73. So it will come as 0.3 meter per second. Pretty simple, just a one line answer. And at last we have to find the detention time. So for detention time, we have to know the volume. So my volume of the basin is L into W into D, that is 18 into 0.73 into 1, that will be equal to 13.14 meter cube. Okay. So my detention time theta will be equal to V by Q, where V is my volume, that is equal to 13.13 meter cube divided by 0.22. I have just changed into meter square per second. Okay, that is equal to 60 seconds, or we can say 1 minute. So very simple. This is my detention time. Is it okay? Guys, are you able to follow this question? Others, please respond. Only Saket is responding. Others, is there any problem with understanding the grid chamber question? Okay, fine. Okay, so we will see one more subjective problem. So these were the answers. Now the last subjective questions. It's the design of the primary sedimentation basin. So a rectangular primary sedimentation basin is designed for an average flow of 10,000 meter cube per day. So the Q is 10,000 meter cube per day. Calculate the length and width of the basin. For this, use the following information. The surface overflow rate should be less than or equal to 40 meter cube per meter square day at an average flow. The side water depth is 4 meter and the basin length to width ratio is 3:1. Also calculate the detention time. and surface overflow rate at design peak flow. So we have been given the question as per design average flow, but we have to find the detention time and surface overflow rate at design peak flow. And the peaking factor is 2.5 is to 1. So peaking factor is 2.5. Simple. So we have to design this primary sedimentation tank. Go through the problem once again. Try to note down the key parameters.
The side water depth is equal to 4 meter
Yes, yes.
means
That is the depth. You can take it as depth of the primary sedimentation tank. Okay. That is the depth of the tank. Okay, we'll see how to solve this problem now.
the surface overflow rate is given, and in the last what is
See, surface flow rate that is given is for the average flow. Okay, that it should be less than or equal to 40 meter cube per meter square per day. That is for average flow. But we have to find the surface overflow rate for design peak flow. So this is the difference. You got my
okay.
point? Please.
Okay, sir.
Okay. Okay. So again, the Q value that is given is 10,000 meter cube per day. We have to find the length. We have to find the width. And given that SOR, my surface overflow rate, should be less than or equal to, this is at average flow. Okay. The depth is given as 4 meter. L is to W is 3 is to 1. Fine. So now we have to find the detention time and SOR for peak flow. Peak flow, and the peaking factor is 2.5. So this is the overall problem. So first we will find the required area. So we will find the required area as per the uh, Q and the surface overflow rate given. So this will be equal to 10,000 meter cube per day divided by 40 meter cube per meter square day. So it will be equal to 250 meter square. So this is the required area for the basin. Now we know that L is equal to 3 times of the width. So my area will be equal to L into W, that is 3W into W, which is 3W square. Okay. So in this way, my W will be equal to root over 250 by 3, which is equal to 9.1. So we can use W as 9 meter. So if my W is 9 meter, my length will be equal to A by W, which is 250 by 9, that is 27.8 meter. So use L as 28 meter. So in this way, we have found the dimensions of our basin as per the average flow. Is it okay? So at last, the actual area A will be equal to L into W, that is 28 into 9, it is equal to 252 meter square. So this is 252 meter square. Now we will find the detention time. So for detention time, volume if we have to find out, volume is LWD, that is 28 into 9 into 4, that is equal to 1008 meter cube. So my detention time theta will be equal to the volume by Q, which is equal to 1008 divided by, this is in,
Sir,
yes, tell me.
what we conclude, required area is less, and actually is more.
Yes, see, the actual area should be a little like equal or more than the required area. So if my required area is 10, I can provide 15 also. That is not a problem.
Okay, sir.
But it should not be too high. Okay, it should not be too high. So instead of 250, we are providing 252. That is okay. That is not a problem. So here it will be meter cube per day. So if I change it into hours, it will be 24 hours per day, which is equal to 2.4 hours. Fine. So my detention time is equal to 2.4 hours. I hope it is fine. So now the third, we will find the SOR at peak flow. So what will be my Q peak? My Q peak will be equal to 2.5 into 10,000 meter cube per day, which is equal to 25,000 meter cube per day. So my surface overflow rate at peak will be equal to 25,000 meter cube per day divided by 252 meter square, which is equal to 99.2 meter cube per day. Simple. So we have found out the surface overflow rate at peak. Is it okay? Pretty simple problem. There is no difficulty, I think. Okay. So I hope you have noted down the problem. We'll move forward quickly. So these are all the. So now we have some multiple choice questions. So we'll quickly discuss it. Okay, we will not waste much time on this. We'll quickly discuss and get done with it. So please be responsive in this multiple choice questions. So the first question says the degree of treatment required for the wastewater depends on wastewater characteristics, desired quality or possible reuse of the effluent, state regulated discharge standards. All of the above. So, what do you think will be the correct answer? So, on what factors the degree of treatment required is depending on?
All.
All of the above. So we should know the characteristics, because as per the characteristics only we will know how, what are the organics or the inorganics present and how much they are present. And then as per my effluent standard, I will check like what is the percentage or the degree of treatment required, and with respect to the state norms. So all the three are applicable. The next question. Okay. Sedimentation tanks are an appropriate example of unit operation, unit process, both A and B, or biochemical process. So sedimentation tank is an, hello,
This is unit operation.
unit operation. Yes, this is correct, because here only physical forces will be acting in the sedimentation tank. That is the force of gravity. With the help of the force of gravity, the particles will settle down and get separated from the system. So all the screening, grid chamber, sedimentation tanks are all example of unit operations. Can someone give me an example of a unit process? Any reactor in which a unit process is happening?
Trickling filter.
Trickling filter, yes, because there is some biological activity happening. So it is a unit process. Okay, now identify the correct statement concerning the advanced wastewater treatment. Disinfection is typically considered as an advanced wastewater treatment process. Selective ion exchange is used for removal of nitrate from secondary treated effluent. Both A and B, and carbon adsorption is primarily used for suspended solids removal from secondary treated effluent. So which of the statements are correct?
So C, option C is right.
Option C. So yes, both A and B are correct, because carbon absorption is not primarily used for the suspended solids removal. Okay, so both A and B are correct. The next question: intermittent sedimentation tank. So which of them is true for an intermittent sedimentation tank? That does it store water for a certain period and keep it in complete rest, allow water to flow at a reduced velocity, also known as continuous flow type tank, or none of the above? So which of the following is correct for an intermittent sedimentation tank? So we have two types of tank. Yes, Satvik.
Option A, sir.
Option A, yes, it will store the water for a specified period of time and it will be in complete rest. If it is flowing at a reduced velocity or at any rate, then it will be continuous flow type tank. So option A is correct, right? Okay. So which of the following is not an assumption of Stokes law? So we have the Stokes law, we have various assumptions. So which of the following is not an assumption? Particle settling is independent of the influence of other particles. Medium is of infinite extent. Reynolds number should be less than 10. Flow is laminar. So which of the following is not an assumption of Stokes law?
Reynolds number is less than 10.
Reynolds number is less than. Sure, what should be the Reynolds number in the case of Stokes law? What is the assumption?
Less than 1.
Less than 1. Okay, that is the correct answer. So Reynolds number should be less than 1. Okay, the surface overflow rate of a septic tank is V. So SOR is V. and the settling velocity is u. The settling velocity is u. So what will be the ratio of the removal efficiency of particles having a velocity less than the critical settling velocity? So my surface overflow rate is v, the settling velocity is u.
Settling velocity by surface overflow rate.
Surface overflow rate. So the option will be C. So C option is correct. That is U by V. Others, is it clear for you?
Yes, sir.
Okay. Okay. So it's pretty simple, but it will be U by V. Okay. The type of settling most likely to occur in a real sedimentation tank is discrete settling, flocculent settling, type 1 settling, type 4 settling. So in a real
It is
sedimentation,
B, flocculent settling.
okay, flocculent settling. Okay, that is correct. That is correct. Anyone else have any issue? Because in any real sedimentation tank, we will see the particles will be slowly agglomerating with each other. So it will coalesce or agglomerate with each other and will form bigger particles. So in any real sedimentation tank, we will seldom see any discrete settling. It will always be a flocculent settling type. Okay. So the surface load, next question, the surface loading rate of a 0.02 millimeter particle is 0.02 centimeter per second. So what will be the efficiency of the removal of 0.024 millimeter particle? So for 0.02 millimeter particle, we have the surface loading rate. So what will be the efficiency of the particle for which the size is 0.024? So we don't have to, if you know the trick, we don't have to calculate anything. By seeing the question itself, we can say the answer. No calculation is required in this question, though it looks like a numerical.
It is C, 98%.
98%. Why do you think so?
So I think 100%.
Okay, Saket has saying, but why do you think it is 100%? Please give me the reasoning. If you are saying 98% or 100%, what is the reasoning behind it? Okay, tell me, which particle is greater, for which we have to find the efficiency or for which the surface loading rate is defined? The particle for which we have to find the efficiency is greater in size, right? So if the particle size is greater than the size of the particle for which the surface loading rate or the critical velocity is defined, that means it will definitely settle because the particle size is more, so it will definitely settle. So any particle which have a size greater than the defined particle will be removed 100%. Okay, is it clear, Abdul? You are saying
Yes, sir. Yes, sir.
okay, so all particles having a size more than the size of the particle for which the surface overflow is calculated are 100% removed. So we don't have to calculate anything. Okay, so this is a match the following type. We have different types of organic and inorganic matters, and we have different types of unit process or operations. So just match the following and tell me which of the options is correct. So you can use a trick that the largest size particles will be removed first. Yeah, tell me.
Option C.
Option C. So yes, we will see. So large floating matter. Large floating matter means the largest size particles will be removed by the screens. Okay, so A will be matched with 4. Then the suspended inorganic matter. Suspended inorganic matters means sand particles or any grit type particles, which have a higher specific gravity, will be removed in the grid chamber. So suspended inorganic matter will be removed in grid chamber. Then we have suspended organic matter. So suspended organic matter means it will be removed with the help of a sedimentation or primary clarifier. And then the dissolved organic matter on which the bacterial action will be done will be removed in the trickling filter. So we are moving from largest particle to the smallest particles. So in that aspect, screens, then grid chamber, then we have primary clarifier, then we can have the biological treatment as trickling filter. So option C is correct. Okay, so this is the last question for MCQ. Which of the following is not an objective of providing an equalization tank during the sewage treatment? So first, balance the fluctuation of flow, balance the fluctuation in concentration, assist in self-neutralization, removal of organic material. So which of the following is not an objective of equalization tank? Just tell me the answer. Which of the following is not an objective? So you should know like what are the important
Removal of organic matter.
removal of organic matter. Yes, this is the right answer because for any equalization tank, it is basically used to assist in the fluctuations. Okay, whether it's a fluctuation of flow like peak flow, medium flow, low flow, or any fluctuation in the concentration of the sewage. So it will help in balancing them. Or you can say for self-neutralization. So option D is the correct option for this question. Okay. So these were all the questions that I had for both the objective type questions and subjective numerical types question. So we will have the next session for week
Sir,
6. Yes, tell me.
please, sir, once explain the settling model.
Settling model, like which aspect do you want to know?
Uh,
Are you talking about the settling velocity distribution or
yes, sir.
settling model?
Sir, velocity distribution and
Did you try the problem given in the supplementary material? There is a supplementary material for week 5. Okay. So have you checked that?
yes, sir, I have. Sir,
See,
even
I will briefly, if you want, I can tell you the settling model. Just
but sir, this type of question is not there, sir.
no, this velocity distribution question is there, right?
Yes, sir.
In supplementary, you want me to explain the settling model, right?
Yes, sir.
Okay, I will. Maybe question I can send you over a mail. One of the question related to this, but I will briefly tell you the concept behind it. Okay,
Okay,
in
sir.
5 minutes. So just wait. Suppose there is a particle which is settling at a vertical speed of Vs. Okay. So what will be the length? And it has suppose settled for a time t. So what will be my length that it has actually covered will be equal to speed into time. So if h is the distance of travel, so it will be equal to my Vs into t. So this is the basic assumption. Like if the settling velocity is Vs and it has traveled for a time t, so the distance it will cover will be equal to h. Now we define something as critical settling speed. Okay, so this critical settling speed or Vc is defined for all the particles of a specific diameter that just get collected. So suppose I want to remove a particle of zero point 0.2 mm. So this is my aim, that I want to remove 100% of 0.2 mm size particles. So for that we have to calculate the critical settling speed. So suppose this height is h and the particle is here. Okay, so my Vc will be equal to the total height h divided by the detention time. So in the proper detention time, it should it should be removed 100%. So it will make a flow like this, and it before the end of the channel it should get settled. Like 100% of the particles of this size should get settled. So this is how we define the critical velocity. Is it okay? So the total distance, it should cover the total height h in the time t. And how will I find the time t? My time t will be equal to my volume by q. Okay. So ultimately it will become q by a, because it will be qh by v, and we can write qh into h, h into a. So h will cancel, it will become q by a. So my settling velocity will be equal to, and what is this? This is my surface overflow rate. So for any particle for which I have defined the size that it should be removed 100%, that critical velocity should be equal to my surface overflow rate. Okay. So for any particle that is of size greater than this critical particle will be removed 100%, and any particle which will be less will be removed in the ratio of h by h, small h by capital H. Is it okay? Do you get any? If I give you any problem, it will be much clearer to you. You can drop down our emails. I will provide you any practice question. So if you solve that practice question, you will be able to understand it better. So this is the settling model. Is it fine? Okay. Okay. So we will meet again on 5th September, same 7 to 9 slot, and we will discuss the problems related to week 6 that time. So please be available on time. Try to join 5 minutes earlier so that we don't have to wait for anyone else. So we can directly utilize all the time and solve the problems. And if you have any queries, you can write to me in my email address shaha19akash@gmail.com. I will try to share the settling model problem with you. Okay.
Thank you, sir.
Okay. You can leave the session if you don't have any more queries. Satvik, Abdul, if you don't have any queries, you can leave the session. Saket, you want to ask anything else?
Okay, sir.
Okay. Abdul, you want to ask anything?
Okay, sir.
Okay, you can leave the session. Thank you.
Thank you.